Hello and welcome to the final part of Lesson 5. This concluding section is going to examine, very much in brief, the topic of viscoelastic flow modelling. We've seen in previous lessons that Cauchy's equation of motion can be coupled to a generalised Newtonian constitutive equation and solved for flow situations that we can relate to polymer processing operations. These included, for example, tapered tubes and radial flow in cylindrical coordinates. Now, obtaining flow solutions for viscoelastic flow problems conceptually takes the same route, but as we'll see, arriving at a solution for flow geometry of interest has additional and substantial levels of challenge associated with it. So let's just remind ourselves what it is that we did when we did some flow modelling before. Typically, what we need to do is to couple material response to conservation of momentum. And so that involves combining an equation of motion with a constitutive equation. Now, since we're talking polymers, that constitutive equation is no longer nice and simple like a Newtonian or a generalized Newtonian, it's viscoelastic. So, what we need as one of our ingredients is an equation of momentum. So there's Cauchy's momentum equation there on the board. And I've highlighted two terms in that. I've highlighted the velocity term in light blue, and I've highlighted the stress term in pink. Now, we need to close that equation and link stress and velocity field, and that is where our constitutive equation comes in. And ordinarily we'd say, oh, it's Newtonian, it's easy, tau equals e to gamma dot, and gamma dot is grad v plus grad v transpose. Now we're in the viscoelastic domain. So there on the board instead, I've put PTT's equation. So there we have a convected differential constitutive equation that has terms of stress, they're in pink, and its derivatives and its nonlinearities, and also terms involving velocity, gamma dot, because we know that gamma dot is simply grad v plus grad v transpose. And so it's these equations that we're now coupling together. Now, if we looked at the simplest problem we can think of, and that was maybe steady shear in a slot, and we looked at PTT in the context of steady shear in a slot to derive an expression for the shear viscosity, then we might be able to tease out the various equations that we need to solve in parallel together. And we might, in this case, for example, get an expression of dp by dx, and we might get an expression in terms of dp by dy. So we've got pressure now varying in two directions. They're equal to derivatives of gamma dot, well actually gamma dot squared and gamma dot, so that's non-linear. And so we're going to have some non-linearities involved in the solution of that. And we're going to have to solve these equations probably numerically, probably maybe using finite differences or finite volumes across a two-dimensional domain. So the key point I want to get across here is that if we're thinking about viscoelastic flow modelling, we need to realise from the outset that this is a fairly complex activity. You're unlikely to be writing your own codes or deriving your own analytical solutions for it. What you are likely to do if you do enter this world is to use pre-existing codes, and so we need to understand a little bit about how they might be limited and about what's actually out there in the first place. So, let's think about analytical solutions first, because believe it or not, analytical solutions do exist for simple flow fields for viscoelastic constitutive models. But even for simple flow fields, the solutions can be really quite involved. They are certainly beyond the scope of this course. However, if you're curious, I'd refer you to the brilliant book by Bird, Armstrong and Hassiger, Dynamics of Polymeric Liquids, specifically Volume 1, which is a volume on fluid mechanics. And there are 3 examples there that give a very good flavour for analytical analysis of viscoelastic flows. So example 7.4-2 on page 371 is the oscillating pipe flow of a white Metzner fluid. Example 7.4-3 on page 377, which directly follows the previous one, so you get a feel for how long these solutions are, is fibre spinning for a white Metzner fluid. And then we've got example 7.5-2 on page 400, which is torsional flow of a convected Jeffreys fluid. And convected Jeffreys is an extension of Maxwell with additional relaxation times. These are long solutions that require a considerably high level of mathematics. That is the disclaimer. So analytical solutions to viscoelastic flow problems are complex. A simpler example can be found in the literature, published by Torres and co-workers in the AICHE journal, and this is all around the extensional flow of Giesecke's fluids, and there's a very nice, simple analytical solution that one can derive for that. I've put the preprint of that paper on Canvas for you. The key message really, though, is that for most practical purposes, viscoelastic flow modelling is probably going to be numerical, and these analytical solutions may give useful validation material against which to check your numerical solution. So let's talk about numerics. Let's talk about some of the problems that you're likely to encounter with numerics. And the key problem that dominated the field for a number of decades when it comes to viscoelastic flow modelling is called the high Weissenberg number problem. Now, the Weissenberg number is a dimensionless group. It's the elastic forces ratio to the viscous forces, and in the simplest possible way we can write this as a dimensionless parameter A, which is a constant that depends on the nature of the problem we're solving, multiplied by the shear rate magnitude gamma dot, multiplied by the relaxation time, or a characteristic relaxation time, of the polymer that's being flowed. And if we think about the units of gamma dot and lambda, gamma dot is reciprocal seconds, lambda is seconds, the product of the two is dimensionless, the constant A is dimensionless, so this is therefore a dimensionless number. And what has been found, and it's neatly summed up by this quote here, is that high Weissenberg numbers, where elastic forces dominate, are incredibly problematic to solve. And Ronald Koenings said in 1986, ever since the early attempts of the mid-1970s, researchers have repeatedly met with an outstanding problem, namely the failure of their numerical schemes to provide solutions beyond some critical value of the Weissenberg number, where that critical value happens to be quite low, 3 or 4 or 5 or 6. And for engineering flows, you might have 10,000 as a Weissenberg number. So numerical schemes were being thwarted by the incredibly non-linear nature of the equations that are being solved. And what we find is that above a certain Weissenberg number, the numerics simply diverge, or they become so unstable that they don't produce a realistic answer. So part of this is an historic point due to computational power. Partly it's related to the resolution of a solution. That is the number of grid cells or the density of the mesh you can put in a flow geometry. But part of it is just the nature of the equations themselves, because they're so nonlinear. So for many, many years, modelling of viscoelastic engineering flows was all but intractable. However, solutions have problems. And about 15 years ago, it was realised that, well, why don't we just do this a different way? If we've got equations diverging to very large values over a very small perturbation, why don't we look at the equations written in logarithmic form? Because then we're not going to get that divergence to large value, which means that we can keep our numerical schemes more stable. And that's sort of the core concept that underlies the log-conformation approach. And it's possible to redraft many of the popular constitutive equations in log-conformation form. Again, the details of this are way beyond the scope of this course, but for the curious, I've put a reference there to go and have a look at. It's very mathematics heavy, but the net result is that you can get stability numerically at high Weissenberg number. So, with suitable compute power and with log-conformation formulation, what you can find is that it is becoming increasingly tractable to start to numerically model engineering type flows containing viscoelastic liquids. So if you're dead set on doing flow modelling for viscoelastic liquids in engineering type geometries, you're going to need to use, in all likelihood, log conformation methods to do it. Or more realistically, you're going to need to choose an existing code that already has log conformation methods implemented within it. So, since we're talking about codes, there are two codes that you might find very, very useful. I'm not going to go into any more detail other than a brief overview to alert you of their existence. The first is a commercial code. It was a commercial code that was developed in Belgium at the University of Louvain-la-Neuve over the course of the mid-90s. It was then adapted by Fluent, and it was then adopted by Ansys, and that is the current code vendor. The code is called Polyflow, and it's a very adaptable, flexible code. Firstly, it has tools that you can fit material functions to experimental data. So it'll do all the types of analysis that we were talking about in a previous part of this lesson. It contains generalized Newtonian fluid models, viscoelastic fluid models, both in integral form and in differential form, and you can solve single mode or multi-mode models in a given geometry. It also allows you to couple heat transfer, including radiative heat transfer, and also heat source terms. So for example, you can approach problems where you have a generalized Newtonian fluid with a specified temperature functionality, including viscous dissipation, which is a topic we're going to be talking about in depth later on in this course, and it will be able to give you a flow simulation for that. One of the really neat tools that's inbuilt into Ansys is what it terms inverse die design or extra date prediction codes. And what this allows you to do is to say, right, extrude this fluid through this shape. What shape extra date do I get? The inverse problem says, I want this shape of extra date. What shape of die do I need with this fluid, with this rheology, to get that result? And that is a very valuable exercise to go through, since it can save a lot of time and a lot of money with the engineering of dies. It also has features for blow molding analysis as well. So being a commercial code, this isn't cheap. Being viscoelastic, you will be wanting to run this highly parallel. I used to run Polyflow on 12 to 15 cores, and that gave a little bit of insight, a little bit of an inroad into some of the problems that I was trying to solve at the time. And that was typically limited to simple differential viscoelastic constitutive equations or thermally coupled generalized Newtonian fluids. Now, there's a new tool, relatively new tool, that's on the scene now, and this is called RheoTool. Now, RheoTool is a plugin to an open source computational fluid dynamics code called OpenFOAM. It's an incredibly powerful platform, and it's all public domain. RheoTool 2 has material function fitting tools. It can do generalized Newtonian and viscoelastic analysis, integral models, differential models, heat transfer, two-phase flows using volume of fluid methods, so you can get some insight into, say, extra date swell, and contains log-conformation formulations of many of the viscoelastic constitutive equations. And of course, it's free of charge to download, compile, and use. However, there's no such thing as free in the world of compute, because you either pay with it with time or you pay with it with money. And this is why I've put both of these tools on the board. Ansys, you pay a lot of money for. It has excellent documentation, highly developed tools, and you can get to very quick results, very good results very quickly. And of course, it has customer support. RheoTool doesn't cost any money apart from the compute platforms you're running it on, but you need compute platforms for both of these tools. But it takes time to know and time to get to use. But it's freely accessible. And so if you invest your time into that, rather than investing money which you may not have into that, then you can start to approach flow modeling from that standpoint. And again, in terms of scale, I used to use RheoTool on a cluster with several hundred CPUs, because that was the scale of problem that I needed. And solution times, and it was fairly old equipment by modern standards, but solution times used to be order of weeks. So these are not quick calculations to run. And so ahead of time, before committing to a flow modeling code, you need to also think fairly carefully about what compute you can afford and about what problems realistically you can solve with the compute that you can afford. Okay, so let's wrap up with a few key points. The key point of this final part of Lesson 5 is to state that, look, viscoelastic flow modelling is a challenging pastime. It is not de rigueur yet still. Newtonian CFD certainly is, even turbulent flow Newtonian CFD is. Polymeric CFD is hard, and it will take time, and it will take investment of either money or time. Analytical solutions to flow models exist. they are complex to arrive at even with simple flow scenarios. One of the key numerical problems you need to be aware of, especially if you happen to find yourself using older codes, is a high Weissenberg number problem. The codes will work for slow flows and certain relaxation spectra, but you may find for the problems that really interest you, the high Weissenberg number problem is a sticking point. However, the thing to look for is log-conformation formulations for constitutive equations, because that overcomes the high Weissenberg number problem and does allow engineering scale flows to be simulated with real material responses. Two codes that you might want to look at: Polyflow with Ansys and RheoTool, part of OpenFOAM.